Despite the massive number of research and tremendous advancements witnessed over the last decade, cancer remains a global killer. About 25,000 New Zealanders are diagnosed with cancer every year.
More people are surviving cancer than ever before, but survival rates languish behind due to the obstacles that existing cancer therapies encounter, such as insufficient drug doses approaching the tumor. As a matter of fact, the incorporation of nanotechnology and cancer cell-specific targeted delivery will be a tremendous asset to the range of anti-cancer therapies and imaging currently accessible. Hi, I'm Khaloud Al Balushi, and today I will explain my research project. Let's take a closer look at the tumor vasculature. Due to the abnormal vasculature where capillaries are compressed, a lower blood flow velocity is observed. This can be used as a biological gradient field to guide the nanorobots for smart tumor targeting. Therefore, the aim of the research is, firstly, to quantify the tumor-induced biological gradient field based upon blood flow velocity using in vivo models. Secondly, study the employment of an exterior steering field to guide the nanorobots. Finally, to determine the measures in the field of search space analysis to study the optimizability of the biological gradient field based upon blood velocity for smart tumor targeting. In order to initiate the process of the research, computational models were used to employ the exact mathematical models to demonstrate how the blood velocity changes in the tumor vessels. The blood flow velocity values were then extracted along 4 different angles. The models were then validated by curve-fitting the velocity values using 1D contour plot. Finally, the models were compared to each other in order to examine the impact of the blood vasculature density on the velocity gradient. These are the results obtained out of the computational models modeled in COMSOL multiphysics software. Model A represents a high vascular blood vessel network, whereas Model B represents a less vascular blood vessel network. The middle region, outlined by a red circle, is the tumor region. It is clearly observed that the tortuosity of capillaries in the tumor region resulted in the following. It limited the circulation zones, and it lowered the overall blood flow velocity across the tumor region, whereas the normal vessels carried a relatively larger blood flow fraction with an increased blood flow velocity. Consequently, the non-uniformity in the blood flow velocity distribution between the normal and the tumor vessels can be used as a biological gradient field. In Model A contour plot, there was a substantial distinction between the blood flow velocity for the normal vessels and the tumor vessels, with the blood flow velocity dramatically dropping when blood approached the tumor and quickly returning to its previous level as it exited the tumor. Model B followed an identical velocity trend to that observed in Model A. However, it is clearly observed that with a less vascular model, the velocity gradient between the blood inflow and the tumor region is significantly lower. 3 new search space analysis measures were proposed in order to address the optimizability of biological gradient fields based on blood velocity for smart tumor targeting. This included number 1, disconnectivity of search space. Number 2, likelihood of counter-current desirable search direction. Number 3, inhomogeneity in different search direction. The application of these measures concluded that for Model B, the less vascular model, firstly, a more discrete search space was observed. Secondly, there is a less likelihood of counter-current desirable search direction. And finally, a significant heterogeneity in various search directions was observed. Finally, this research concluded the following. Blood flow velocity can be quantified using in vivo models and can be used as a biological gradient field to help nanorobots detect cancer tumors. Using 1D contour plots, tumor distance can be calculated based on blood flow velocity. The less vascular blood vessel network possesses a lower gradient and a more discrete search space. This research helped me accumulate an extensive knowledge about the biological processes involved in the cancer growth. I hope that these discoveries will lead to more effective and targeted treatments and prevention strategies in the future. Thank you.